But NASA is much, much greater in extent. It actually has five what are called mission directorates. Aeronautics research does research to help move people and cargo throughout the atmosphere around the Earth. Space technology develops the technology for people to live and work in space. Human spaceflight has two directorates. The space operations involves things with humans in low Earth orbit. So the International Space Station and the capsules that take astronauts back and forth from there all fall out of there. And then there's the Exploration Systems Development Mission Directorate, and that involves deep space exploration. So that's the Artemis program to return humans to the moon and then eventually to go on to Mars. And then finally, last but not least, of course, is the Science Mission Directorate. And that's the part that funds all of the science stuff. And the Science Mission Director is actually split into five separate divisions: heliophysics, which studies the sun; earth science, which studies the earth; planetary science, which studies everything in the solar system except for the sun and the earth; astrophysics, which studies everything outside the solar system; and then finally, the biological and physical sciences division does cross-cutting research among all the other divisions focused on biology and physics related things. So whenever you hear somebody speak about planetary missions, you know we are all funded from the Planetary Science Division. So the next question to ask is, how do we choose how to explore the solar system with different types of spacecraft? It may seem that it's haphazard because you hear about flybys to one place, rovers on another one, orbiters, etc. But it's actually very well thought out. We do it in a very phased approach with what's technically possible, what we have the engineering skills to do and build, what's affordable, what Congress will give us the money to do, and then accomplishing the easy missions first successfully, then on to more complex missions. And this list you see on this slide here is the order of those missions in increasing difficulty, complexity, and cost. So the simplest is a flyby. A spacecraft flies by a planetary object, takes pictures, collects data, transmits it back. That gives us our initial reconnaissance of what an object is like. Then you want to go into orbit. And the advantage of orbiters is they go around the planet spins on its axis as the orbiter is able to acquire data from all longitudes to get a global data set that allows a global assessment of what a planetary object is like. And then, of course, once you know about it from orbit, then you want to go down and land. And there's a variety of ways you can do that. Hard landers, they descend, they collect data on the way down, they smack into the ground, the instruments are broken, so they're somewhat less useful. Ideally, we want to use soft landers, and those are the ones that have retro rockets or parachutes or airbags or something so that it lands softly, the instruments all survive, they deploy, and you get those wonderful 360-degree panoramas so you can get data at your landing site. But as often happens when you land on a surface, you see something interesting over there, and you wish you had mobility, and that's where rovers come in. So rovers have legs or wheels to move around on the ground, or if it's an object with an atmosphere like Mars or Saturn's moon Titan or the planet Venus, you can use some sort of a drone or balloon to move around through the atmosphere and thus visit multiple places on the surface. The next hardest and most expensive is robotic sample return, where you actually collect a sample of rocks or dust or ice or atmosphere, put it into containers that you then send back to Earth, where we can study them more effectively in the labs on the Earth. And then finally, the hardest to do and the most expensive thing are crewed missions, where you send humans to orbit and land on planetary surfaces. Now, this chart here shows you the status of solar system exploration as of right now in 2025. You see across the top the various modes of exploration from telescopes to crewed missions, and you see the objects in our solar system starting with Mercury closest to the sun all the way out to Pluto and the Kuiper Belt. And what you'll notice on here is that the first column, telescopic observation, is completely filled in because that's how everything was discovered, through telescopes. You'll also see that the second column is completely filled in, starting with the Mariner 2 flyby of Venus in 1962 and concluding with the New Horizons flyby of Pluto in 2015 and one of the cold classical Kuiper Belt objects on January 1st of 2019. We have completed the initial reconnaissance of the solar system. Now, as you move further to the right, you see Whereas you get to these more complex missions, you start to have it less well filled in. White on this chart means things from the past, things that are done. Blue and green are things that are paid for, are built, and are either going to launch or are in flight right now. Things that are orange or yellow have been proposed but are not yet funded by Congress. And you can see as we go across the chart, a lot of the inner solar system, small bodies, comets, and asteroids, and the inner Jupiter and Saturn of the outer planet, giant planets, they've all been visited by orbiters. We have flight missions, Europa Clipper on its way. That's going to be sort of like a Europa orbiter, but without being in Europa orbit. JUICE, that was mentioned in my introduction, that's going to be a Ganymede orbiter in the end. Galileo and Cassini, of course, and Juno out there. As you move further, you see, landers to rovers. We have Curiosity and Perseverance operating on Mars. The MSR Mars Sample Return is orange because that has not been funded yet, and that is a very hard thing to do robotically. And then, of course, the only place humans have landed so far is the Apollo program to the moon, although Artemis is coming up fast. So, what I like to say is our goal as planetary scientists is to completely fill in this chart, to completely explore the solar system, and then we will be able to boldly go where no one has gone before, as they say in my favorite TV show. So, with that preliminary background here, let me go on and talk about the subject of this talk, the Psyche mission. First, I'll provide a little background on asteroids. What are they? Where are they located? And why do we care about an asteroid named Psyche? I'll go through our mission, its objectives, its instruments, its operations, the fact that we launched a couple of years ago, and what we hope to find when we get there. And then we'll review some things from other small body missions with a look ahead, and then conclude with a Q&A. So, asteroids, what are they? They are minor planets, protoplanets, rocky planets, usually with diameters less than 500 kilometers. They're mostly irregularly shaped, like this image of 21 Lutetia, imaged by the European Rosetta mission. They're mostly composed of silicate rock and dust and maybe some volatiles. And in this context, volatiles means ices, mostly water ice, maybe carbon dioxide or other exotic ices as you get farther to the outer solar system. So most asteroids are located in the main belt found between the orbits of the planets Mars and Jupiter. However, there are populations throughout the solar system. There's a population called Trojan asteroids that are at the Lagrange points, 60 degrees ahead and behind the planet Jupiter in its orbit about the Sun. The Centaurs occur between the orbits of Jupiter and Neptune. And then the ones that we often hear the most about are the near-Earth asteroids of several different varieties. And those are the ones who have orbits that come to or cross those of the inner planets. And there's about 4,700 of those potentially hazardous ones because those are the ones that could impact any of the terrestrial planets. There are close flybys by NEAs by the Earth all the time. Occasionally, we have some interesting extrasolar stuff. 3I Atlas was mentioned, that comet. That's its trajectory through the solar system and the animation there. And I will talk a little bit about that toward the end of the talk. 16 Psyche is a main belt asteroid. So, what we know mostly about asteroids comes from the reflected light spectra from telescopes and from the analysis of meteorites, because there are many meteorites that are pieces of asteroids. And so they've been classified by about 14 different types based on their telescopic spectra. C-type is rich in carbon-rich minerals, about 40%. S-type are silicate or stony minerals, silicate minerals. D and P, dark and primitive, those are the Trojan asteroids. They have not been visited yet, but they're the target of our sister mission, Lucy. V-type, those are volcanic minerals like what you would see in basalts like at Hawaii or Mount Etna. That is basically the asteroid 4 Vesta, which was visited by Dawn last decade. And then you get to the M-type. And in this case, M stands for metallic. We think those are iron nickel cores, and they could be the source of some families of iron meteorites. So by comparing asteroid telescopic spectra with meteorites in the laboratory, we've come to the conclusion that the asteroids are basically rocks that never coalesced into a planet in the main belt. The gravitation of Jupiter is just so massive, it keeps a planet from forming in that location. And occasionally, main belt asteroids are tossed out by Jupiter's gravity into the inner solar system. So spacecraft exploration of asteroids, it's really they have been what you one might call a tag along or something that's seen as a planetary mission was going to another destination. You see, the first two asteroids that were visited, 951 Gaspar and 243 Ida, were visited by the Galileo Jupiter orbiter during its solar system cruise on its way out to Jupiter. And I was there when those images returned. I was in grad school at ASU at the time. It isn't until you see the missions in bold on this chart there are actually missions dedicated to visiting asteroids. And the first one really was just 25 years ago, the Near Earth Asteroid Rendezvous that orbited Near Earth Asteroid 433 Eros. And actually, they were able to soft land it on its surface at the end of the mission. The Japanese and the US have been sort of major leaders in this with Hayabusa 1 and 2, Dawn, OSIRIS-REx, and then finally the two missions in green, which are in flight right now, our sister mission Lucy to the Trojans, and then Psyche. So this picture here is a montage made by Emily Lakdawala of the Planetary Society, and it shows all of the asteroids and comets that were visited prior to the Dawn spacecraft arrival at asteroid 4 Vesta in July of 2011. And you can see here that the asteroids are, as I said, very irregular. They have dents in the surface. Those are impact craters. Some places you might see linear features, lineaments, could be pit chains, and in some you will see boulders. Some appear to be very big solid rocks. Others appear to be rubble piles like Bennu and Ryugu. And then, of course, down in the corner, you see the comets, which are dirty ice balls, icy dirt balls. They have a lot more volatiles in it. So, but there is sort of a continuum between comets and asteroids. Now, in terms of size, this is a size comparison comparing the planets Mars, Mercury to the Earth's moon and to dwarf planet Ceres and asteroid Vesta. And you can see we're basically talking about a lot smaller bodies. The key question is, do planetary-like processes occur in objects as small as Ceres and Vesta? And as the Dawn mission showed last decade, the answer to that is yes. The question is, how small can you go and still get those processes? So that brings us to Psyche. So Psyche was the 16th asteroid discovered. It is the largest M-type asteroid in the solar system. These pictures show you basically the shape of the asteroid. It's not round. It's sort of potato shaped. And you can see the dimensions of it there. It was discovered by the Italian astronomer Hannibale de Gasparis of the Naples Observatory back in March of 1852. 16 Psyche orbits at about 2.9 astronomical units, which is at the outer edge of the main belt. Takes about 5 years to go around the sun once, but it rotates on its axis very quickly in about 4 hours. Now, what is Psyche composed of? Well, it's a M-type asteroid, which means it probably has a significant component of iron, nickel, metal. Its density is measured from, various observations suggest it's higher than for most silicates, but not super high. It appears to have, we think, some sort of a porosity, which would make sense if it's been bombarded by materials. There's been evidence perhaps of silicates there, maybe carbonaceous material, perhaps even water ice on the surface. The two most meteorites that closely resemble the telescopic spectra of asteroid 16 Psyche are Gubja and Yeshevo. And I have pictures of those. And you can see those are metal-rich iron meteorites. So how big is this asteroid? Well, here you see Lutetia was the big one that I showed you first thing in the first couple slides. You see some of the other asteroids going down smaller. And then you see asteroid Vesta there. If you were to put it gently down on the surface of the Earth, Vesta would cover all of the state of Arizona or New Mexico. So that means that Psyche is actually somewhat smaller than that. And so how big is that compared? Well, since you guys are on the East Coast, you'll appreciate this. Psyche is about the size of the state of Massachusetts if you leave off Cape Cod, or if you've ever driven through Arizona, it's the distance between Phoenix and Flagstaff up the I-17. So this is a big asteroid. It's smaller than Vesta, where we know we had planetary processes. So that is a question. Could they have actually occurred on an asteroid this size? So whenever you come up with a planetary mission concept, you need to come up with a set of driving questions or science objectives to justify NASA's expense of using taxpayer dollars to justify building this mission and going to this target. In the case of this asteroid, the driving question is 16 Psyche the core of an asteroid parent body? We have not seen a planetary core directly before. So we came up with a set of science objectives for it. Is Psyche a core, or is it a piece of metal that never underwent melting, left over from the formation of the solar system? What are the relative ages of the different parts of its surface? Because as you can see in the image down there, it is heterogeneous, different shaped on the surface. Do small metal bodies incorporate light elements like expected in the high pressure core? Did Psyche form under more oxidizing or reducing conditions the Earth's core? So this is the idea that by studying one of these exposed planetary cores in space, it could inform us about Earth's core, which is much harder to study because it's deep down in the center of our planet. And then finally, what is the unique topography of this metal world? So the concept behind how this asteroid might exist that we wrote into our original proposal when we proposed this to NASA is the idea that as the gas cloud from the solar system was forming, the gas condenses into solid particles that eventually accrete together to form pebbles to cobbles to boulders to planetismals that come together to make planetary embryos and then finally planets. But what happens if you have one of these differentiated planetismals with crust, mantle, and core, and you knock off the crust and mantle, and you might have an exposed planetary core? And that's what you see in this animation here, where you had impacts knocking off a crust and mantle. You have a molten core exposed to space. It's going to cool and crystallize. You're just going to be struck by impacts. Since it's molten metal, it's going to be able to be, and it's rotating, it'll generate a magnetic field. If it might have sulfur inside, because sulfur is often found within planetary cores, but sulfur doesn't mix well with liquid metal. It wants to separate, and that's what the yellow stuff extruding out of this thing is coming out onto the surface over there. So that's the concept of what we thought Psyche was, and that's what we put into our proposal when NASA ended up selecting us. So what does our spacecraft look like? Well, it looks a lot like an Earth orbiting satellite here. You see a guy here for scale with our spacecraft, and this is without the solar panels. I'll show you that in a minute, but basically you have a cubic box that has the fuel tanks, it has the computers, the avionics, and all the other subsystems you need, as well as a high gain antenna, a low gain antenna, and the various locations of the instruments, the gamma ray and neutron spectrometer, the magnetometers, and the cameras, which I'll talk about, as well as propulsion, cold gas thrusters, and ion propulsion, which I'll talk about that as we go on through. So if you put the solar panels on and spread it out, you see the guy for scale, it would basically, our spacecraft is the size of a tennis court. And if any of you ever travel to Tempe, Arizona, come to our campus in Arizona State University, in our main planetary science building, we have a full-size model of the Psyche spacecraft hanging above our gallery of space exploration. So, how did this all come about? Well, basically, a group of scientists led by the woman who became our principal investigator, chief scientist, which is Dr. Linda Elkins Tanton. She and some folks got together and started talking about sending a mission to visit this large M-class asteroid, 16 Psyche. So it took several years to develop the mission concept and proposal. And when NASA asked for mission concepts, we submitted a proposal. And we competed with about 25 other missions. And we were part of a short list that was accepted. I think there was maybe 5 or 6 that were accepted. And we got funding, $1 million of funding to develop a more sophisticated, more detailed proposal. So that was submitted. And then that was studied by NASA, compared, cost evaluated, risk evaluated. And fortunately, on January of 2017, Dr. Linda Elkins-Tannon got the call from NASA saying our mission was selected. So, that began a 6-year process of formulation and development through preliminary design, critical design reviews, building the spacecraft, and getting it ready for launch. And so this is where you see on this timeline here, it's not an insignificant task to actually develop these types of robotic planetary missions. So we completed construction of the spacecraft back in 2022. We were slowed down by the COVID-19 pandemic. Here you see a picture of me. This is with the spacecraft in the clean room at the Jet Propulsion Laboratory in Pasadena, California, before the solar panels were attached. And in the image on the right, you might be able to see at the top a couple of tubes right here sticking out of the face there. And those are actually the multispectral imagers, the instruments that I work with. So we shipped the spacecraft to the Kennedy Space Center in April of 2022 for the launch in October. However, there was a problem. The guidance, navigation, and control software had been developed, but it hadn't been tested in time. As I said, it was slowed by the COVID-19 pandemic. And you don't want to launch a spacecraft if you think the guidance, navigation, or control (GNC), is not up to speed if it hasn't been tested yet. So we were granted a 1-year launch delay so we could really check everything. And so the spacecraft remained at the Kennedy Space Center. The software was all developed and tested. The spacecraft was checked out. And so we finally got approval to launch about a year later. Now, this image here shows the spacecraft all buttoned up, and this silver tube out the front side there is one of our science experiments called DSOC. It stands for Deep Space Optical Communication. And the concept is you use a laser to transmit information as opposed to the radio waves that are picked up by the big dish telescopes, radio telescopes. And this was an experiment to see if we could use lasers to transmit information out from the main asteroid belt. And I'll mention that later. So after the 1-year launch delay, we go down to the Kennedy Space Center, and it's the week of October 9th through the 13th, where we were down there to get ready for launch. You see the Kennedy Space Center, you see the Psyche sign. We had all of our undergraduate interns out there talking to people. Some of us were giving talks there about the mission to visitors at the Kennedy Space Center. Here you see myself with, to my immediate right, Professor Jim Bell, who's the lead of the imager, and to his right in the purple is, with the white hair, is Dr. Linda Elkins-Tannon. She's the PI of the mission, along with some of our colleagues. And we're out there at the launch pad, because you see the launch pad there on the left, and at the top of that white fairing, at the top of the rocket there, is where the Psyche spacecraft was located. So we were out there, and then, Friday, October 13th, launch day came, and we were able to launch. So I think it'll say it.
9, 8, 7, 6, 5, 4, 3, 2,
So 35 years in the planetary business, and this was actually my first rocket launch. So my wife was recording this, and it goes off there, it disappears in the clouds, and it comes back here. But very, very exciting. So our spacecraft launched on a SpaceX Falcon Heavy, and you notice the boosters are a little bit scored there because they were reused. It's wonderful we live in a time where we can reuse our rocketry components. And you hear there the time from when it launched. You can see it, but you don't hear it. It takes a while for the sound to catch up with the person there. But it was a really awesome experience. So this is a summary video of that launch again here.
And here we go with the final seconds of launch. 5, 4, 3, 2, 1, engine ignition. And liftoff. Liftoff of Falcon Heavy and Psyche on a mission to a metal asteroid in deep space to study the building blocks of our planet's inner space.
Power and telemetry nominal.
Data is looking really good.
Side booster separation confirmed.
Great shot there. The side boosters coming off the rocket.
Landing burn has started.
Here it comes. Perfect landings for them both.
Psyche payload separation confirmed.
There it is. The Psyche spacecraft going off into deep space. We have a signal that says, hey, I'm here, I'm out in space.
So that was pretty cool. I actually had to wait until the end of the day that day when we got together with the Imager team down there at Port Canaveral, and they said, "Oh yeah, the solar panels deployed, everything is going great." So it was we also saw a second rocket launch there from our dinner restaurant there at Port Canaveral. So two launches in one day after a 35-year career without seeing any. So anyway, our spacecraft, it launched successfully October 2023, and this graphic here is our trajectory. So the chemical rocket launches it, and then while we're out in space, we fire up the solar electric ion propulsion. And that propulsion allows us to spiral around the sun as we go outward. And we are basically right now we are here where the star is located. We're coming back in for a Mars gravity assist in May of next year, which will give us a momentum boost, and then we're going to go back out into the main belt to arrive at asteroid Psyche in August of 2029. So it takes a lot longer when you use ion propulsion, and the reason why we use it is it's a very low mass fuel. And in space, with space exploration, mass equals cost. So the more mass, the more cost it is. So to make this spacecraft affordable to do what we do, we use this ion propulsion, which uses the low mass fuel, but with a very low acceleration. So it takes longer to get where we want to go. But, we can do it for lower cost. On this graphic, you notice those dots, those pink dots here. That's the time that we were testing the deep space optical laser communicator. And we wanted to see if we could send information from all the way out in the main belt. It had been done from Earth to the space station, from Earth to the moon, from Mars distance, and this took it all the way out there. So that is a viable technology in the future. So this is just a graphic about the ion propulsion, which I've sort of already talked about. You see the blue flame of the engines. And as I mentioned here, the xenon fuel is this ionized there. It has very low acceleration, but it also has low mass. So you're saving money and saving cost on mass, but it's going to take longer to get where you're going to go. That's basically what all this is about. And this was pioneered by Maxar Technologies, formerly Space Systems Loral, who have a lot of heritage using this type of propulsion on Earth orbiting satellites. So this is their first deep space mission that they've been involved with. So when we get there in August of 2029, this is how we're going to do it. We're going to use a series of orbits from higher altitude to lower altitude. Each is optimized for different instruments. And because of the launch delay, we have to split our B orbit up into two parts because when we arrive, only the equatorial region and the southern hemisphere are going to be lit up by the sun. We're going to have to go back up to that orbit at the end of the mission to get the northern hemisphere in sunlight. That way we'll be able to globally map the surface. And that's sort of what it's saying on this chart. You don't need to read all this, but the thing I would point out is that, we are going to take images at all four of these different orbits, and it's going to get better and better. So our first orbit is going to be about 35 meters per pixel, which is similar to what we had at Ceres on the Dawn mission. And all that gradually will get down to about 4 meters per pixel in our highest, our lowest altitude orbit. But each of these orbits is optimized for a different set of instruments. So what instruments do we have on our spacecraft? Well, we actually have three of them. We have imagers, magnetometer, and gamma ray neutron spectrometer. So the imagers are led by ASU, and they were built by Malin Space Science Systems in San Diego, California. And we have two for redundancy, and they are basically going to take the pictures of the surface, and we're going to do it looking for the shape of the surface, what we call morphology. We're going to look for brightness or albedo. We have color filters to look at it in color, and in particular to look for evidence of silicate and sulfide minerals because sulfides are found in association with metals. And by looking at the surface at different look angles as we do different orbits, we'll be able to construct a topographic map of the surface through stereo imaging. The magnetometer is led by MIT, Massachusetts Institute of Technology, and it was built by the Danish Technical University, which is north of Copenhagen, Denmark. And these fluxgate magnetometers can measure magnetic fields to a sensitivity of 0.1 nanotesla, which is very high precision. And so if there are any parts of the asteroid that are magnetic, or if it has a global magnetic field, we'll be able to determine that. The gamma ray and neutron spectrometer is built by the Applied Physics Lab at Johns Hopkins University near Laurel, Maryland. Gamma ray spectrometers measure elemental abundance, so the amount of iron and nickel and silicon and potassium and thorium, all that good stuff will be measured, whereas a neutron spectrometer measures hydrogen abundance, and that hydrogen can be either in water ice or it could be in clay minerals or something like that. So we'll be able to detect those materials on the surface. And then finally, using the telecom system, we can do a gravity science investigation. And the idea is when you fly over an object that has a little bit more mass, it pulls the spacecraft down a little bit. If it has less mass, it goes back up a little bit. You can measure those differences in the Doppler time delay of the radio signals very precisely. And from that, you can build up a map of the interior of the object. If this is not just an exposed planetary core, if it actually is something that still has crust and mantle and core, we'll be able to determine that through the gravity science experiment. So this just shows the wavelengths of the filters here. And you can see we have a broadband clear filter as well as these different filters for looking for silicate minerals that might be in a crust and sulfides associated with metals. And here just shows you, since we're a mapping mission, you basically just orbit and you cover the surface. And these are the footprints of the images, very coarse at orbit A and very fine down at orbit D. We'll get global coverage on orbits A, B, which is B1 and B2, and C, whereas the orbit D, which will be equatorial, we won't get quite as good a coverage. So this is just a graphic. It's one of these ideas, these concepts about these objects in the asteroid belt being hit and run impacts. And sometimes you can hit an object and knock all the crust off of it, but also you could hit it from a side and maybe part of the impactor turned out to be the source of asteroid 16 Psyche. This is just an animation that shows something like that. So here's an artist concept painting of the asteroid based on the telescopic shape model that we put into the original proposal. And the idea is that here's an exposed iron nickel core with maybe some sulfur that was extruded when it cooled and crystallized. But this is just one possibility of what this asteroid could be. Could it be something that crystallized from the inside out, from the outside in? Could it be a rubble pile, or could it be a big chunk of unmelted metal? Now, during the time that the mission was developed, our planetary astronomer friends have been pointing all manner of telescopes up at this asteroid and trying to get more information for us. So these two artist concept paintings here are a couple of more ideas about what it could be. On the left, you have a metal asteroid that's probably heavily fractured, but it's got a lot more silicate gunk covering it. That's a possibility. On the right, you see something even more different. This is where you would have silicate and metal that is very intimately mixed, like in a palisite meteorite. And I'll show you a picture of that if you haven't seen it. So that could also be a possibility of what this asteroid could be. Or it could be something totally different. So how will we determine what it is? Well, there is no single one piece of evidence that's going to say this is what the asteroid is. You have to assemble all of the evidence, and it's going to require all of our various instruments and data. We're going to have to see, do we have sulfide, iron sulfide minerals on the surface? Do we see certain levels of nickel content from the gamma ray spectrometer? Do we see any evidence of magnetic fields of any type there? And when you start to put this together, you can make decision trees, like this one here. And, depending on what information goes, it can help limit the possibilities about what this asteroid could be. So that's the approach that we're going to take with it. Now, as a geologist, I'm interested, what does geology look like on a world made out of metal? So what you see here is an example of a high velocity impact. This is from the vertical gun, NASA's facility at NASA Ames Research Center, which is in near San Francisco, California, where you have a gun that shoots a projectile at different types of targets at a hypervelocity. And this was shot at a metal ingot there. And you can see there it formed an impact crater, but the impact crater rim sort of freezes as it's being formed, and you get this raised rim of solid metal that forms there. And you also get fracturing down underneath the crater in this particular experiment. This is a palisade. So these meteorites are what we think occurs at core mantle boundaries of metallic asteroid parent bodies. So the yellow color there is actually grains of olivine surrounded in a matrix of metal. So this is what you would expect near a core mantle boundary. This is a possibility about what Psyche could be. It could be any of these things. So this cat video here, this was one of the tests they did of the DSOC experiment, the Deep Space Optical Laser Communication. So they sent this was on board the spacecraft, and they used their laser to send this cat video all the way back from the distance of the main asteroid belt. So, this experiment, it's basically a technology demonstration, was very, very successful, and demonstrating that we knew how this new method of communication that we can use as we continue to explore further out in the solar system. So what have we been doing since launch? Well, every 6 months we have to do a calibration check on our instruments. So this was the first one we did in July of 2024. We pointed the camera at the Wishing Well star cluster. I'm sure some of you have looked at that through telescopes there, just to test to make sure our cameras are working, and you can see worked fine then. In January of this year, we looked out at Jupiter, and as you can see here in the inset, we not only saw Jupiter, but you saw the 4 Galilean satellites of Jupiter. So that was our test then. And then back in July of this year, we looked back at the Earth and the Moon, and you can see in the inset there, our Psyche imagers were able to see the Earth and the Moon separately. And then most recently, with Comet 3I Atlas passing through the solar system, we were able to image that, and I'll just talk about that in just a moment. So let me say something about some other exciting research on small bodies. You probably all have heard of the OSIRIS-REx mission, which was an orbiter and sample return from near-Earth asteroid Bennu. You see spinning down there. That is most definitely a rubble pile asteroid made up of big chunks of rock. So they sampled it, put it into a sample return container. It returned to Earth a couple years ago, and it's been analyzed down at the Johnson Space Center in Houston. And you can see they found some really interesting things here, from precursor molecules to amino acids to nucleobases to clay minerals. So whatever the parent body of this asteroid has basically the building blocks of life in it. I find that astounding that something from the origins of the solar system had some of these complex materials in it. So I mentioned our sister mission, Lucy, going to the Trojan asteroids of Jupiter. You can see the graphic right there. We're not there yet, but we did do 2 flybys of main belt asteroids. November 2023, the S-type asteroid Dinkinesh, which actually has its own moon. Yes, asteroids can have their own moons, and we saw that there. You see that at lower left. And then in April of this year, the C-type asteroid Donald Johanson, you see an image right there. Now that's probably a binary object that came together. It's got 2 lobes on it. So that's very exciting. And then the next target is going to be in 2027 when they start exploring the Trojan asteroids there, starting with Eurybates, and then onward to the other Trojan asteroids. So let me talk about 3I Atlas. This is an interstellar comet. It's from outside our solar system. You see the part of the trajectory there. NASA basically said any one of our spacecraft in space that would be capable of imaging it, let's target it, let's get information on it. In particular, because when this asteroid was at perihelion, we cannot image it from Earth. So a lot of different spacecraft you see on that table were brought up to try and image it. And fortunately, that press conference about that was just a couple of days ago, if you listen to it there. Here's the Psyche image. This was from the New York Times showing this. So over the course of several times, we imaged it 4 times there, and you can see the arrow pointing at that very fuzzy dot there. So it's not much to look at, but what some of the other instruments do show is it did appear as a comet. It is not an alien spacecraft like some have suggested, but it's got a nucleus and it's got a coma. This is from the Mars Reconnaissance Orbiter when it was at Mars. It passed by Mars at like 0.2 astronomical units. Psyche saw it at 0.35 astronomical units. And then our sister mission actually saw it from further away, but you can see hints here. It looks like there was a little bit of a tail. This is not going to be as bright as like Halley's Comet in 1910 because of, it just wasn't that close to the sun, so it couldn't develop as much of a tail. But it was exciting that, we were able to see it. And some of the heliophysics spacecraft, Stereo A and SOHO, I think got pretty good images of it as well. So, well, I would be remiss talking about asteroids if I didn't say something about asteroid mining. And we think it's pretty clear that asteroids will have valuable resources to help us build our spacefaring civilization. Now, just as an intellectual exercise, our PI did an experiment just based on the size of 16 Psyche and the amount of iron, nickel, and platinum group elements that are in typical iron nickel meteorites. And if it was all made up of that stuff, that this asteroid would be valued at 100,000 times the gross national product of all nations on Earth, or 10,000 quadrillion dollars. Now, obviously, that's not right, because if you brought all of that stuff back to Earth right away, the metals market would crash, and so it would be very, very different. But the point is there could be valuable resources out there, and there are companies like Planetary Resources and others that have tried to investigate how those could be mined. Now, it's not going to be as simple as sucking an asteroid in on one side and a space station popping out as the other, like you see in the top graphic. And it is going to take decades for humans to figure out how to mine on microgravity. But the potential resources there, from building materials to helium-3 like in the surface of the moon, from solar wind to water ice, which can be used not only from oxygen and liquid water, but also for rocket fuel. These are all things that can be useful as we help building our spacefaring civilization. So it's something definitely to look forward to. So we've reached the end of the talk. Let me summarize. Asteroids are the rocky remnants from the formation of the solar system. On January 4th of 2017, NASA selected ASU, Arizona State University, to lead a Discovery-class robotic mission to visit M-class asteroid 16 Psyche. NASA Psyche spacecraft, just like the Dawn spacecraft before it, uses solar electric ion propulsion to move through the solar system. Saves on mass, saves on cost, takes longer to get where we're going. Our spacecraft carries 3 instruments: visible imager, magnetometer, and gamma ray and neutron spectrometer, plus the gravity experiment. We successfully launched on Friday, October 13th of 2023. We are cruising through the solar system now, heading toward our Mars flyby in 2026, and a planned arrival at our asteroid target in August of 2029. So, what you see on the right of this slide is a shape model, is showing the shape of Psyche from telescopes, and the map at the bottom is a combination of visible and radar albedo. And the main thing you take from that is it's heterogeneous, it's different. So we don't know what the surface is exactly, but we know we're going to see different things on different parts of the surface. So that's what we're going to do. And here, I'll just leave this up here. You can do a screenshot of that QR code. That goes to my laboratory's website where we have digital posters, planetary posters, and we have a double-sided poster for asteroid 16 Psyche, as well as all of the other NASA missions that I have worked on. So, with that, I am going to stop sharing and I will be happy to take questions. Thank you very much for your attention.
First off, first question. In the very beginning, you said that dinosaurs didn't have the ability to detect and deflect an asteroid. I mean, could we have deflected something the size of that asteroid right now?
Yeah, that's an excellent question. Could we have deflected something the size of the asteroid that killed off the dinosaurs? And that is something that is kind of hard to know. We are just now entering the era of planetary defense, and you probably heard about the DART mission led by APL a few years ago, the double asteroid redirection test. And the concept behind that is there's near-Earth asteroid Didymos that has an asteroidal moon named Dimorphos. And what we did, we sent a spacecraft to crash into it, basically be a kinetic impactor, to see if we could alter the orbit of that asteroidal moon. And we actually did by, I think, what, 13 minutes or something like that. So we demonstrated that yes, it is possible to use kinetic impact to alter the course of an asteroid. Now, the bigger the asteroid, the greater the danger. So the further out it is, the less effort it takes to change it. Because if you alter a trajectory when it's very far out, just a little bit of change and you'll miss the Earth entirely. So, could we have deflected the Chicxulub impactor? I don't know, but what's important for us is that we do develop this technology, and the OSIRIS-REx mission has been renamed OSIRIS Apex and it's going to go fly by the asteroid Apophis, which is a potential hazard at some point in the future. So we are just at the very beginnings of planetary defense. And I think it's good that we are, pursuing that as well as identifying all of the potentially hazardous near-Earth asteroids. There's a telescope mission, NEO Observer, that's being built to do that.
Okay, well, also, just going on that, could we fling another asteroid at a larger one?
Yeah, that's the question is what would be the ideal type of thing to do to deflect an asteroid? Would one asteroid impacting another do the job the right way? That might be overkill. Plus, also, if you hit something like that, you could produce a lot of fragments, and then you just have a bunch of smaller things coming at you, potentially. Once again, it depends on how far away it is. And, the farther away it is, the less effort it takes to deflect it. So what we've done so far is just, smash it with a spacecraft, yeah, a kinetic impact. An asteroid hitting another asteroid would be another form of kinetic impact.
A different question also. You were talking about the ion drive being cheaper to launch and all that, but it also adds extra mission control time, which adds extra costs. It still comes out ahead.
Yeah, it does still come out ahead. We think it's worth the effort. Um, you know, uh, if we tried to launch one of these missions with conventional propulsion, it would have required so much mass, we probably couldn't do it as a Discovery class robotic mission. Discovery class missions are, basically $500 million or so. But if you had all that extra fuel on board, you need a much more powerful rocket, which would increase the cost. There is only so much money available to the Planetary Science Division, and there's an awful lot of targets to go to. So you try and figure out the optimum between, what mission architecture you want to do, and waiting a few more years, Once you're launched, you're pretty much in a cruise phase that's pretty dull actually, until you get to where you're going. So that seems to be the model that we've found to be acceptable. A few years, 3 years, 4 years, 5 years, 7 years, the longer the cruises are, if for outer solar system missions. So I think most people can live with that just to have a mission rather than being unaffordable trying to do it with chemical propulsion.
Question about your cruising here. Is your magnetometer picking up magnetic flux from magnetic field variations during the solar wind?
Yes, the question was, is the magnetometer on and are we picking up any variations in the solar wind? Yes, the magnetometer and the gamma ray and neutron spectrometer have been on since launch, after they were commissioned and tested, and they are on during the cruise phase. And they are monitoring, they can monitor solar flares, they monitor galactic cosmic ray outbursts. I think they detected something that indicated a couple of black holes collided. So yeah, those instruments are actually collecting data during the cruise phase. The imager only is collecting data when we do our 6 month PMCs, periodic maintenance and calibration activities. And we will be collecting, I think all the instruments will be collecting data during our Mars flyby next year.
My question is about the laser communication experiment. Is that in visible light or infrared? And is that involved with the detectors that go with Palomar?
Yeah, I don't know the exact wavelength of the laser. I bet you could probably look that up online if you just did a Google search for DSOC or Deep Space Optical Communication Psyche. What I can tell you is they have an instrument mounted, I think it's on the Mount Palomar telescope, that shoots a laser up to the spacecraft can receive information, and then the device on the Psyche spacecraft is a laser that sends it back, information to Earth. And the further away you are from the Earth, the less the data rate becomes, because it was actually a pretty high data rate when it was closer to Earth, and then way out there, it basically dropped from megabits per second to kilobits per second out there. But we are still receiving information. So this first test of using it out there has been successful in that regard.
Thank you all. Thank you so much, Dr. Williams. That was wonderful. And we will be.
My pleasure. Thank you very much. Glad you all enjoyed it there. Maybe at some point our paths will cross again.